This video will provide a brief introduction to Jacobians. We shall start with reviewing the very basic definition of differentiation as we learned in calculus. We have a function from R to R and some point A in R. We want to say that f is differentiable at A. The definition was that this limit exists finitely. And if I call that limit m, then m is the derivative of A at that point A. Now, why exactly do we use this definition? The reason can be seen pictorially. Suppose this is the graph of fx and this is the point A. In that case, if this curve is smooth, in the intuitive sense of smooth, then if I look at only a very small neighborhood of this, the curvature will not be apparent and it will seem that this is almost like a straight line, just like when a man stands on earth. If we consider the viewpoint of the man, then he thinks that he is standing on flat ground. Of course, there is a curvature here, but it is not apparent to that small man who is looking at only a very small neighborhood around himself. And similarly, when I take a very small neighborhood, this just looks like a straight line. This straight line, as we know, is called the tangent. Now, if I want to make this precise, that looking over a very small neighborhood, this straight line and this curved line are indistinguishable from each other, then we can use the following mathematical trick. We know that any such line must have equation y equal to fa plus some m times x minus a. This is the general equation of a straight line passing through the point fa, assuming that the line is not just purely vertical. So this m right now has nothing to do with that m. It is just an arbitrary slope. To say that this line it becomes indistinguishable with that line, Newton and Leibniz suggested the following thing. They said, look at the difference between the fx and the value on the line. Obviously, this will go to 0. This should go to 0 as x comes closer to a. So, I am allowing x to hover very close to a. But that is not enough. They further suggested that I need something stronger. Even if I divide it by the difference x minus a, so here is your x, and then this is what I have shown here as x comes very close to a, even this thing should go to 0. If that happens, that captures the intuitive idea that this straight line and these curved lines are indistinguishable from each other when you restrict your attention to a small neighborhood around A. Now, quite interestingly, this definition and this thing are actually equivalent. So, you just rearrange things and you will see that if there is an m which satisfies this condition, that must be precisely this m. Conversely, if there is m according to this definition, then that m must satisfy this. And that is why we use this as the definition of derivative in the one-dimensional case. So, in summary, this is the entire picture of one-dimensional differentiation. This captures the intuition. This is the starting point of everything. And this is a corresponding simpler version, and these two things are basically equivalent. Now, the same thing or a rather similar thing works when we are working with multivariate situations. Suppose this is from Rn to Rm. In that case, we again start with some a, now a vector in Rn. So, we want to say what is meant by this function being differentiable at that point a. Then, surprisingly, these cannot be generalized easily this one may be generalized quite easily, retaining the same intuition. Here, of course, I will be working with H and 0. This is in Rn. Similarly, I will put arrows here. Now, this has an arrow. As a result, this must be a matrix. Remember that this is in Rn, so this matrix has got to be m by n, and you cannot divide by a vector, but what we want to say is that this becomes very small, so I divide by h naught. If this is also the 0 vector, this is the 0 vector in Rm. If this holds for some matrix M, which may depend on that particular point, we say that F is differentiable. Now, we call this M matrix quite naturally the derivative matrix. Now, this form is more complicated than this form. So, in case of one-dimensional thing, we had these two equivalent forms. This was preferable in the sense of computation, because here M is on one side and everything other in terms of F was on the other side, and here M is deep inside that complicated expression. So naturally we want to find an analog of these in case of multivariate differentiation, and we can get some such thing which looks like this. If I look at the ijth entry of M, then it will be partial derivative del fi by del xj at that point A. Quickly understand how we are considering I and j. Because f is a function from Rn to Rm, so f basically consists of m component functions. So the ith component function I am writing at x1 dot 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 up to xn. So this is the ith component function partially differentiated with respect to the jth variable and evaluated at the point A where we are performing the differentiation. Now there is a big difference between this and what we have seen for the one-dimensional case. And that is, in that case, these two things were equivalent. If this holds, then that holds. If that holds, then this holds. But in this case, if this holds, then definitely this will hold. That is, if you have some m for which this holds, that m must be given by this. However, even if you have this thing, that is all the partial derivatives exist at A and you can construct a matrix M, that does not necessarily mean that that M will satisfy this condition, which is a much stronger condition than mere existence of the partial derivatives. As a result, we need a new terminology for the matrix whose ijth entry is given by such partial derivatives, and that term is the Jacobian matrix. It is not enough to just know the definition of the Jacobian matrix. In order to use them, we have to also have a feeling for the geometric interpretation of the Jacobian. When we are working with fr to r, then the Jacobian matrix is basically 1 by 1 matrix, which is the derivative, and we know its geometric interpretation as the slope. But when we move to higher dimensions, then that interpretation changes quite a bit. Suppose we are at some point A, and we move a little bit to a plus h. As a result, the function changes from fa to fa plus h. Now look at the difference that you see in the function, which is fa plus h minus fa. Now the definition of differentiability basically says that this is approximately like m times h. In other words, this is approximately a linear transformation of h. So this linear transformation plays the role of the approximating straight line, which we call the tangent. Now, how do these linear transformations look like? In order to visualize linear transformations, think of the graph paper where we have got this vertical and horizontal lines, and these are all squares. Now, if you apply a linear transformation, that is, if you apply the map from every x goes to some mx, here we are working with 2 by 2 matrices, then the result will be all these lines will be somehow distorted, because to every point I am applying this transformation and then I am joining these lines back again. Then the picture will be something like this. So all these squares have now become parallelograms, and excuse my bad drawing, all the parallelograms should look just identical. And the shape of each parallelogram will be determined by the particular matrix M that you are using. So the nature of M can be seen geometrically from the shape of these parallelogram tiles. So if you change M, this shape will change and all the tiles will be of the same shape. So every parallelogram here remains a parallelogram. In particular, I am showing the squares, they have turned into parallelograms. Now, when we are working with a general differentiable function, locally it behaves like this. So at every point, near to every point, the tiny squares drawn near to that point will convert to parallelograms. But if you consider a different point, there the M may be different. So again at that point, the local squares will again convert into parallelograms, but possibly to a differently shaped parallelograms. To understand, take this example. I started with R2 with a nice regularly spaced grid, and I applied a function from R2 to R2. As a result, this grid changed into something like this. You can easily see that this is a nonlinear function. Now I consider, say, this point, which has gone to this point. So locally you see the squishing has taken place like this. So if you look at it locally, if you take a bigger view of this region and you take a bigger view of this region, so just imagine that there is an ant living here, and if we look at the microscopic neighborhood of that ant, you will see these tiny regular tiles in the floor of the ant's house. But after you have done this transformation, these things will transform as these parallelograms. So because you are looking at only a small neighborhood, they are parallelograms. They are approximately like parallelograms, and all the parallelograms are of the same size. So locally, the ant who lives here will think that the transformation is a linear transformation which converts these tiny squares to these kind of parallelograms. Now imagine what happens for the ant who is living, say, here. Now this ant has now moved to this place, and again that ant also initially had regularly spaced tiles like this, but now after this application of the function, what he sees will be like this. So he says that there is not much squishing really, things have just turned a little bit like this, but this ant will say no, things have been squeezed in one direction and really made skinny. That is because the linear transformation that this ant thinks it sees is the Jacobian at this point, and what this ant sees is a Jacobian at that point. So at every point, the local ants believe that they are seeing just a linear transformation, only the linear transformation is different at different points. And this is much like the situation that human beings experience with our earth. So here is the earth, and this guy stands here. This guy thinks that the earth is flat and it looks like this. This guy also believes that the earth is flat, but he thinks that that line is this. So both of them have the same experience, similar experience, in the sense both of them believe that the ground under their feet is flat, but the particular flat thing with which they approximate are different at different points. Similarly, both the ants believe that they are looking at a linear transformation, but the linear transformation is different. And that linear transformation is given by the matrix which is the Jacobian at that point. Now let's take a closer look at this same example. So I start with R2 and I will look at only a single point. Instead of drawing all the vertical and horizontal lines, I will draw just the horizontal line through that and the vertical line through that. So the ant who lives here has all these little tiny tiles aligned with these two lines. Now let us see what happens when I apply the function f to this. This point will move to, say, some point here. This line through it will now become something like this, and this line possibly becomes something like that. Now, the ant who sits here, who is now sitting here, sees only a small portion. As a result, it does not understand that this line is actually curved. Instead, to that ant, the line seems to be this tangent. Similarly, this line appears to be that tangent. So, if you consider a tiny little square here, to that ant, it will just seem that this has converted to this parallelogram. Of course, it is supposed to be very small, but I am drawing it to a sizable extent. So, you see, these two things, these two tangents actually determine the shape of the tile, and these two tangents, you can see quite easily, gives you the two partial derivatives, because here I am moving along or moving parallel to the x-axis, that is, I am keeping y fixed and letting x change, and then I am taking the derivative at that point. So this thing basically gives me the partial derivative of f with respect to x. And similarly, this gives me the partial derivative of the other thing. So here I am considering one side and here I am considering the other component, and as a result, I am basically getting the Jacobian matrix over there. Now, you can just take your time to figure out that if I consider my Jacobian matrix, which will be like this, which is evaluated at that point A, then this column, the first column, is precisely this little vector. And similarly, this column is precisely that little vector. When I say exactly that little vector, I mean this is the direction of that thing. Now, you can see how the Jacobian can be interpreted as giving the shape of the converted tile. Now, in many cases, we are interested in this area, and that area will be given by the determinant of this matrix. So, the determinant of the Jacobian often plays a very important role. So, basically the idea is, if you start with a unit square, in that case, what will be the area after the transformation? That will be given by the determinant of the Jacobian. Now, this is not entirely precise because I said it is very small, and now I am saying it is unit square. So, do I want to say that 1 is a small number? No, I really do not mean that. I mean that if you take a very tiny square, then this area will be whatever area you start with times the determinant of the Jacobian. So, determinant of the Jacobian is basically the new area divided by the old area. And in the limiting sense, as this becomes smaller and smaller, these things come closer and closer. And it may be negative. In case this new area is negative, which means it's a signed area, that is, you just flip the thing. If you flip it, then it's considered as a negative area. If you do not care about that flipping, you just want its actual area, that is the geometric area, you can work with just the absolute value of the determinant. That is used very much in probability theory when you are doing change of variable in a double or triple integral. So that is basically the idea behind Jacobian. So the Jacobian gives you the way a multivariate function will squish the grid locally at a point. It gives you the shape, the Jacobian matrix gives you the shape and orientation, and the Jacobian determinant gives you the amount of area stretching or contraction. So if this is more than 1, things are being stretched out. If this is less than 1, things are being contracted.